All right, hello. This is problem 2A2 in the textbook, page number 94. We are tasked with finding the angular acceleration of the pulley right here, the acceleration at point B, acceleration at point C. Now, in doing so, we are given the big radius of the entire disk, which is 0.15 meters, the little radius of the pulley, 0.075 meters, and the angular acceleration at A right here, and that's the magnitude of it, and that's 75 meters per second squared. So in order to find all this, we're going to add 2 extra points. We're going to call this centerpiece 0.00, 0.0, and then this top piece right here, C prime. So we first need, in order to find all this, we need the angular velocity of the pulley. So in doing so, we could start off with V of C prime equals V of O. Gamma, which is what we need to find, across R C prime O. So 0.000, moving, that goes to 0. And we know that gamma right here is gamma K at RC O. That is equal to R. So plugging all of this in, we get V C prime negative gamma R sine fraction. And actually using numbers and plugging in what we know, we get 1.5 meters per second equals gamma little r, which is 0.075. From there, we get gamma to be equal to 20 radians per second. So we need that in order to find the rest of this, the angular acceleration. So, section this off. Hopefully you guys can see the bottom part here. Finding the acceleration, we're going to start with the acceleration at point A, acceleration at O, gamma squared RA slash O, plus alpha, that's what we need to find, across RA slash O. So we know that RA slash O is equal to negative R J hat, and we know that alpha here is equal to alpha K hat. We know that omega already is 20 radians per second. The acceleration at O is 0. And we know the magnitude of the acceleration at A. So in order to do that, you can start off with the magnitude acceleration at A squared using Pythagorean's theorem equals gamma squared big R plus alpha big R. That's squared. Simply plugging in and solving for alpha, we get alpha equals square root of acceleration at A squared minus omega squared R. All that's squared. All of that is little over big R. So we know all these numbers here. Plugging that in, we get alpha to be equal to 300 radians per second squared. That is the end of part 1.
All right, this is part 2 of example 282 from the textbook. So in the previous part, we found that omega was -20 radians a second, and we found that alpha was 300 radians a second squared. Now we can take these numbers and we can plug them into our acceleration equations. Yeah, acceleration p is equal to the acceleration vector of O plus alpha times cross product of RP/O minus omega squared of RB/O again. Now we know from the given pulley that A of O is going to be 0. And so then finally we can do the cross product, find that acceleration vector of B is going to be is equal to 0 plus alpha of k hat times cross product of -r and the j hat, that's -r. Excuse me, that's in the I direction, not the k direction. And then that is subtracted from omega squared times -r in the I hat direction. So finally, when we do the cross product, we get the resultant vector of the acceleration of B to be omega squared r in the I hat minus r alpha in the j hat. Then when we plug in all of our givens into this, we'll get the acceleration vector at B is equal to 30 I hat minus 22.5 j hat. Now going on to solve for the acceleration vector at B, or at C, we have to solve for the acceleration at C prime. And the acceleration of C prime is equal to the acceleration vector at O plus alpha times the cross product of R C prime/O minus omega squared R C prime/O. And so again, we know that the acceleration vector at O, that's going to be 0. And so now we can solve for it to be the acceleration vector of C prime is equal to alpha in the k hat times the cross product of r C prime/O. And that is just going to be r in the j hat minus the omega squared times r in the j hat again. And now we can substitute in all the variables that we know, or pardon me, we can do the cross product of this to find the acceleration vector at C prime is equal to negative alpha times r in the I hat minus omega squared r in the j hat. Then we can set our acceleration vector C is equal to the acceleration vector at c prime, but only in the I hat direction. So this results in the acceleration vector at c is only equal to negative alpha r in the I hat. Now, when we substitute in everything we know, we'll get the acceleration vector of c is equal to negative 22.5 radians per second squared, and acceleration vector at b is also radians per second squared.